here I start something which is really, really classic here. Not fashionable, just really classic. Okay, Rayleigh-Bernard convection. How many people studied convection already? One, okay. Okay, so I start off with this really simple thought exercise here. We have, okay, everybody knows, okay, what convection is more or less. You know, you have a radiator. Even here in Australia, it gets cold and you have radiators. Am I right? Yes? Okay. So above the radiator, you know that the air goes up, right? You know, and you know that the hot air rises. Everybody says that. Okay. But is it really hot air that rises? No, it's actually light air that rises. And it just happens that hot air gets light. Okay. So, but that aside, let's look at what happens and what is, what's going on. First of all, everybody knows there's gravity, right? Of course. And the gravity is acting on all the air in the room, right? And so why isn't all the air in the room falling to the ground? Why can we breathe? Well, you can't answer this. Or maybe you can. But why isn't all the air on the ground? I mean, everybody knows Navier-Stokes, and I'm not telling you anything that's outside of Navier-Stokes. No, forget the temperature gradient for the moment. Let's not talk about temperature. I mean, you could, but let's not talk about that for the moment. Let's say it's all the same temperature. I meant to say this to begin with, before I mention temperature. So, yeah, why isn't all the air just falling on the ground? And you don't invoke some you know, van der Waals or something. That's not in Navier-Stokes. Why isn't all the air on the ground? Why?
Pressure gradient?
Yes, very good. Right. It usually takes people a long time to get to that. That's right. And yet that's not quite the right answer. I mean, it is. But why is there pressure? Because the pressure in an incompressible is such as to. But yes, that's right. You have in Navier-Stokes to, yeah, it takes usually most classes a very long time to get to this answer. And you'd think, you know, it's such an obvious thing. Why is there, you know, when I first started studying, yeah, why is there air up here, you know, and not there? The answer is that we, in a situation like this one, there's an established pressure gradient, and at each point you have your air that feels the gravity and the pressure gradient that acts exactly opposite. And so each air molecule just stays there, balanced between the pressure gradient up and the gravity down. You know, you don't usually think about that, but there it is. Yeah, that was too fast. Usually people are stumping, reading for one. They say van der Waals, they say this and that. Okay, so at each point you have that. You have this at each. So that's what's being drawn here. Is you have your gravity and your pressure gradient that counteract one another. Now, suppose we know that gravity acts more for heavier things. So supposing you have your cold fluid and, excuse me, what is it I'm trying to say? Yes, you take two fluid particles. This is Rayleigh's old argument. You take your two fluid particles and you interchange them. You're cold, and you imagine that the particle keeps its temperature. So you have this heavy cold particle, and you have this warm light particle, and you've interchanged them. You imagine that they've kept their temperature, at least for a little while. I mean, it's eventually going to diffuse, but for the moment, okay. But they find themselves in this region where the pressure gradient is not what it was when they were, where they were before. It's in a new place. So supposing, indeed, you start off, you have a situation like this one here, where you're cold here, and so you have here this, and you're hot here, and you feel here, so you're cold at the bottom, so here's your cold, heavy particle, and it feels a big gravity and a big pressure gradient, right? And here, up you have this light particle, and it feels this little gravity and this little pressure gradient. And now you're going to switch the two particles. So you put this one up here, and you put this one down here, and you say it's, for a little while anyway, it's conserved its coldness, and hence its heaviness, and so it has this big gravity. And this one here has conserved its properties, so it's up here. And yet, it finds itself in an environment where the pressure gradient was such as to counteract where it used to be. And so you add those two together, and you get a net force which is upwards, like this one. So this little guy, who you move down, feels a force back up, a restoring force. And here, if you add the gravity that it feels with the pressure gradient of its environment, you'll find it feels a little force that's downwards. So this guy that you moved up feels a restoring force back. Okay, so this situation is such that it kind of reverses itself. It has a tendency to reverse itself. And you take the opposite situation where you have cold on top and hot on the bottom. And again, you have your heavy guy here, your light guy here, and it finds itself, it's in the environment. The pressure gradient is such as to counteract it. You switch them around, it keeps its property, it's the same thing. You do a sum of these two things, and it feels the net force is upwards. So you took this white one, you moved it up, and it feels a force upwards. And you have this one that's heavy and cold, and you brought it down, and it feels a force that's downwards. So this motion tends to be increased, and that's what an unstable situation is. It moves a little, and that makes it want to move more. Whereas here, it reversed itself. So this is the basic explanation of why if you put a hot or light fluid on the bottom and a cold or rather heavy fluid on top, that's unstable. This is a movement which tends to perpetuate itself. That was Rayleigh's original argument in 1916 or something like that. And that is the basic explanation. So the steps of the class, and we'll probably get to the third item or so, are kind of very classical things. Boussinesq approximation, basic state, non-dimensionalization, linear stability. It's supposed to be an illustration of how you take a big physical problem and you reduce it to what we were doing just before. Okay, so Boussinesq approximation is the simplest way we can study convection. We assume that, yes, density depends on temperature, but linearly. And that is, of course, true sufficiently locally. Every behavior is linear if you're looking over a small enough interval. So this is true as long as your temperature difference is sufficiently low. And the governing equations are Navier-Stokes equations with the following additional effects. You have the gravity term, which is also called buoyancy. This, everyone knows, gravity is g times rho, right? But if rho depends on t, then you call it buoyancy. Then as for temperature, you have, it gets advected and diffused. Okay, so this is all simple and things that those who study Navier-Stokes or in engineering or anything have seen before. And you have the boundary conditions, the velocity is 0 here and here, and the temperature is hot here and cold here, or rather it's one temperature here and one temperature here. And there is a solution to these equations, an obvious solution to these equations, which is u equals 0, so that everything here goes away, this is 0, and now you just pick grad p to counteract g rho of t, where rho of t is this linear function. Okay. You can't choose t equals 0 because you have these boundary conditions that are different. It has to go from 0 to 1. But what you can do is take a linear profile in t, because then the Laplacian will go away. Is that the solution? Yes, it is, right. The Laplacian goes away because it's linear. And then you just have to take care of the rest, and there won't be any time dependence because this is going to be a fixed point. So this is the search for the fixed point that we talked about in the very beginning of dynamics. What you do is you look for a fixed point, and which is a fancy way of saying we're just looking for the base, motionless state. So as we said, t, the base one, known as stars, has 0 motion, has a linear gradient, and we don't really need anything else, but we can find the density. The density is, of course, just a formula of the t. It's a linear dependence on the t. And then the hydrostatic pressure is such, just as we said there, it counteracts the buoyancy force. It's just such that grad p, what you want is grad, meaning, in this case, d by dz of p, so all you have to do is integrate this up in z. Okay? So when you do that, you have this linear function of z, and you get a quadratic function of z for your pressure. Okay? So they counteract each other, and there, you're finished. And now we write temperature as the base state, plus the thing with the hats. That is like when we wrote, in the previous class, we wrote x bar plus epsilon, and we looked for the fate of the epsilon. So we expand the buoyancy, and we write it, we have T star plus T hat, minus, that's the formula for the rho, and we expand the, and then the term, the grad P minus GP rho, when we take out the base state with the stars, we get something that's, remember these counteract one another, that we did that on purpose, so we end up with just this red term that has to do with only the perturbations. That's like our epsilon from before. The temperature advection, remember T has two pieces, the T star and the T hat. The T star is linear in Z, so U dot grad T star grad is now going to be a Z derivative. So we're just going to get minus T naught minus T1, as in here, over D, times U in the Z direction, because this is only in the Z direction. And then we have the advection of the temperature. And so these are the final governing equations for the quantities P hat and T hat, and U. We don't need a hat on the U because the base state is 0, so the U and U hat are the same. And these obey homogeneous boundary conditions because the base state already absorbed the inhomogeneous ones. And since I won't, okay, non-dimensionalization is, I mean, some of you know how to do it, some of you don't, probably, but it's kind of dull, so let's just skip that part and say that of those three equations that we have, we're going to write them, where did I get them? Yes, we're going to write them here. And here we see that we end up with only two parameters. This one being called the Prandtl number, this one being called the Rayleigh number. And these are the final equations over here. And these are the definitions of those parameters. This is a ratio of diffusivities, because viscosity, you can see, is the diffusivity of momentum, and then kappa is the diffusivity of temperature. And the Rayleigh number measures the difference in temperature, basically. Okay. And now we can put on boundary conditions, and the simplest possible thing to do is to have periodic boundary conditions horizontally, and in the vertical direction, as we said, we have we've fixed the temperatures, and since the temperatures, then, okay, we recall that what we're doing is looking for something having to do with these hats, and these stars already have the inhomogeneous boundary conditions. That means that for this to satisfy the inhomogeneous boundary condition, if this satisfies the inhomogeneous boundary condition, then these better have 0 boundary conditions. Right? So it has 0 boundary conditions. And then W equals 0 means you cannot penetrate the plate. And now there's two possibilities for the tangential velocity. You can either allow tangential velocity or not. Allowing tangential velocity is a mathematically simpler thing to do. You allow it. You allow slip, which is not realistic, but it turns out to be simpler. Or you can have them be rigid, in which case the tangential velocity is 0. It can't move because the plate isn't moving. And with incompressibility, you turn the conditions on the tangential velocity into conditions on the vertical velocity. That is to say, if you have said that you have no velocity in the u and no velocity in v here, then that means that you also have no variation of the u velocity in x and no variation of v in that direction, because you fixed them to be 0, and that tells you that you have no variation in w of the in z of the vertical velocity. If you do free surfaces, you use the same kind of reasoning, but you end up the free surfaces, you have to say something about the unit V. You say that there's no tangential stress, and so, for example, this is one of the, no, there are two equations that talk about the tangential stress, the one this way and the one that way, and you end up with an equation that says W equals 0, not dz W equals 0, but W itself equals to 0. And why is this convenient? Because if you take, trigonometric functions, say sine functions, are 0 here, and their second derivatives are 0 here, but not their first derivatives. So saying that something is 0 here and that its first derivative is 0 here rules out, say, sine functions, which are the simplest things to do. So these free slip boundary conditions allow you to use the sine functions. And maybe I should stop here. I don't know that. Let's see. Yeah, it doesn't seem. Yeah, let me stop here. Yeah, we'll go on tomorrow. Okay, and let me give an outline, a flavor of what's we're going to get to. We're going to get to the Lorentz equations. Remember the butterfly, and that's why I asked you. We're going to study it in detail, and if you want, you know that it's always. Again, as I say, I wouldn't have given homework problems, except that apparently those of you who are taking it for credit are going to get an exam, and everybody wants to, you know, if you're really going to get an exam, then obviously you want to do something to prepare for that exam. Okay. One of the questions in the homework is to analyze the Lorentz model in the same way that we just did for the bifurcations, the steady bifurcations, and the Hopf bifurcations. And you know that of course, nobody wants to do things themselves. So everybody has plenty of things to do already. But you know how much more you learn when you do something yourself than when you're shown it. So, and tomorrow you will see the answer for these Lorentz models. So wouldn't you learn a whole lot more if you tried to do it yourself tonight? Again, I say this, this is what I always say. I teach for the student that I was. And the student that I was would not have done anything if I wasn't made to do it. And so this is what I suggest, is that you actually do those problems before tomorrow, because it will teach you a whole lot more than not doing them, and then you'll be ready for the exam later on. Again, it's not my idea, but if you're going to take an exam, then this is a way to study for it. There. Okay, so I think we'll stop here.
Right.
Thank you.